Hello students, in this video we'll discuss uniform convergence of a sequence of functions. Given a set S, or let's say X, a subset of R, we say that a sequence of functions, Fn, n goes from 1 to infinity, and where each Fn maps X into R, converges uniformly to F if for every epsilon greater than 0, there is an n in n such that, and here's the important condition, such that Fn of x minus f of x is less than epsilon. This is true for n greater than or equal to n and all x in x. And all x in x is an important condition over here. So that every single x inside this x has to satisfy this inequality, not just one particular x. So let's do sort of a classic example of this. So here's a theorem that we're going to prove that really proves why we care about uniform continuities. Here's a proposition. If Fn are continuous on X and Fn converges uniformly to F, then F is continuous on X. Okay, great. Now, of course, what's happening over here is that I am using the fact that there's a uniform convergence. I'll show a counterexample to this after we do the proof. So sometimes we use this notation with a double arrow sign for uniform convergence. So the uniform limit of continuous functions is continuous. That's an important thing. So here's the proof. Let's let epsilon be greater than 0. And pick n in n such that Fn of x minus f of x is less than epsilon over 3 if n is bigger than or equal to n capital. That follows from the uniform convergence. Now I know that Fn for any such n is going to be continuous at this point x, right? So we also know we can find delta, choose delta, such that what? Such that f n capital, this n capital of x, and let's see, and let's pick a point. Let's pick y in x, okay? F of x minus this point Fn of y can be made less than epsilon over 3 if x is in the neighborhood of y, right? So if, in other words, if x for all x minus y less than delta. Okay. So since we're continuous at this point y, I know that for any x in a delta neighborhood of this point y, I have this estimate over here. Okay. So now let's estimate this function f of x minus f of y. Okay. So f of x minus f of y. Okay. We're going to throw in a whole bunch of points over here. So the first thing I'm going to do is I'm going to add and subtract in an Fn of x. So I'm going to need a couple different things over here. I'm going to need an Fn of y over here. I'm going to need an Fn of x to make use of this estimate, and I need an Fn over here. So I'm going to put in Fn, and I'm going to put an Fn of y. So let's do that. So what's going to happen is that this is going to be 3 terms. So I'm going to write this is equal to f of x, and then plus minus Fnx plus minus Fny, and then of course minus y, minus f of y. Okay, so I have those 6 terms over there. So what I'm going to do is I'm going to break this into parts now, right? So there's going to be one part of this is going to be an Fn of f of x minus Fn of x, f of x minus Fn of x. That's one term I'm going to get. Then I'm going to get this Fn let's see what we're going to have over here. So I have an fn minus fn of y, then plus, I'm going to have an fn of y minus f of y. Okay. And remember that this, by our uniform convergence, that this is going to be true. This is our uniform convergence. This is true for all x in x. Okay. And the final term over here, the final term is just going to be what I have left. I have a negative fn of y and fn of x. So then plus fn of x minus fn of y. I have these three terms over here. And so let's estimate each of these three terms. So let's look at this first term over here. So how can I handle this first term? So this first term over here, I can use this condition because once we're past n, for any x in this range, that's going to be less than epsilon over 3. So this term over here is less than epsilon over 3, and that comes from uniform convergence. That's the uniform convergence. Okay. Let's look at this term over here. This term over here is also in this regime because y is a point in this, y is a point in x. So this term over here is less than epsilon over 3, also by uniform convergence again. And this final term over here, fn of x minus fn of y, well, I know that by the continuity, that is less than epsilon over 3. So these terms over here are less than epsilon over 3 by continuity. So that's continuity. So all total we get less than epsilon. And this is true provided what? Provided that x minus y is less than delta. So if x minus y is less than delta, f of x minus f of y is less than epsilon, and that shows that the function f is continuous at y. This implies that f is continuous at the point y. And therefore, the uniform limit of continuous functions on a set the uniform limit of continuous functions on a set converges to a continuous function on that set. Thank you very much.